Alright, this is question number 10. Hopefully the sound works on this one. I apologize for the last one, but it should be obvious what's going on. I'll re-record if I have time. Alright, this one is 3.7 CW, number 10. A ball is thrown at 80 meters per second at an angle of 70 degrees from the horizontal toward a 120 meter tall building 60 meters away. We'll talk about that in a minute. So what we just want to look at right now is our projectile. So we have an initial velocity here, and we know our motion looks like a parabola. That is a terrible parabola. Do not quote me on that one. Alright. That is really, really bad. I don't like that. Alright, restart. Alright, so our motion looks like a parabola. I'm just going to draw it in. That looks better. Alright, so we know we have a delta x here. In the very top of the flight, we have y max. There we go. Alright, so let's look at our givens. We know our initial velocity is 80 meters per second, and our angle theta is 70 degrees. Alright, so the first part is simply asking what are the components, x and y, of the initial velocity. So we know velocity is a vector, and a vector at any angle can be broken down into components. So we're just looking for this side and this side. So v naught y and v naught x. So simply part A is looking for your trig rules. So v naught y is v naught sine of the angle, and v naught x is v naught cosine of the angle. Alright, so for part B, we're looking for the max height. But first we have to solve for time, because we can't do anything, and when in doubt, solve for time first. So we want to solve for time of the flight. We know this is a symmetrical flight. It doesn't say it lands on a ledge. It doesn't say it's being thrown off a building. So we're assuming symmetry here. So we're going to write symmetry. And we know for symmetry that means our final velocity is going to be equal to the initial velocity. And I wrote it for the components because, spoiler alert, in its opposite directions. So that's negative right there. Alright, so if we look down, the easiest way to get time is Vy equals V naught sine of the angle plus GT. We know this, we know this, we know this, and we can make assumptions about this Vy at the end of the flight here. So we can say T equals VFY minus V naught sine of theta all divided by G. That gives us, so if we say this is negative here, we can say negative V, I'm going to write it as V naught sine of theta minus V naught sine of theta. And this is just applying this definition. So the final velocity in the y direction is equal to negative V naught in the y direction, all divided by G. So if we plug that in, we get minus 80 meters per second sine 70 degrees minus 80 meters per second, 80 sine 70 degrees minus 9.81 meters per second squared. Alright, plug and chug, and we get 15.33 seconds. Alright, and that's our total time, right? Because we solved for the final velocity in the y direction. Well, didn't solve for it. We made assumptions about that VF down here, and so we went from the initial to the final position, and so that's our total time there. To solve for y max, we're going to assume we're just talking about halfway up. So our y max, we are going to make two assumptions: that our Vy at that point is 0 meters per second because it's not going any higher or getting any lower, and our time is just to go up, which is half of the total time over here. So 7.67 seconds. Alright, we use equation number 3, and we say y max is 1/2 g time to go up squared plus v naught sine of the theta time to go up. Alright, in the effort to make this video one part, I'm going to just say plug and chug. So we've defined everything up here, and so when we plug that in, we get